Yeah, so question 11, we'll do question 11, 13, 14, 15 is our next group. Question 11, this redox reaction, identify the oxidized and reduced species as well as the oxidizing and reducing agents in this reaction. Got iron 3 oxide, reacts with carbon monoxide to make iron and carbon dioxide. And so in this redox reaction, we'll focus on the iron first, right? So in Fe2O3, we can split that up to say I've got 2 iron and I've got 3 oxygen. Oxygen's always -2, so that's -6. I need to have a +6 here. So each iron is 3+ because that needs to be neutral. We know iron ends up neutral because it's just elemental iron. Carbon monoxide. In carbon monoxide, we can split this up into carbon, oxygen. Again, we're just going to assign a charge, right? We know this is not ionic, but we can assign a charge to say oxygen is still always -2, which means that carbon is 2+ in this case to balance out and be neutral. And then in carbon dioxide, all right, again, we're just going to assign a charge. So I've got 2 oxygens, -2, that's -4. All right, so carbon here needs to be 4+ to balance that out. So now we can kind of see this as a redox reaction. All right, I've got 2 irons at 3+, right? They must gain 6 electrons total to go to 2 iron, that's 0, right? Gain of electrons, that's reduction, which makes this oxidizing agent. And then carbon monoxide to carbon dioxide. Carbon, we've got 3 carbons at 2+ each. They go to 3 carbons at 4+ each. How do they do that? How do they become more positive, right? Each carbon loses 2 electrons for a total of 6 electrons lost, which is oxidation, right? Oxidation is done by the reducing.
I don't think I learned that much. Like,
agent. All right, so now oxidized species is what, right? The oxidized species, you could say carbon, you could say carbon monoxide, you could write out the, carbon monoxide as an answer, that's fine. The reduced species, let's see if I can write the reduced species, you could write out iron, you could write out iron oxide, all right, Fe2O3, that would work. Oxidizing agent, we could do the same thing. We could say the Fe2O3, or if you wanted to say iron or whatever, all of those should work as possible answers. And then the reducing agent, again, was carbon, carbon monoxide. All of those should work as possible answers for those. You only need one answer, so don't put in all of them. Yeah, we're headed to question 16, and then when we're asked just for the oxidized species or the reduced species, okay, cool, good question, right? This has come up in emails. You don't need the coefficient, right? It's just asking what is being oxidized, what is being reduced. You don't have to say, I have 3 of them in the reaction or 2 of them in the reaction. So you're right, you don't need the coefficient in the answer. It's just asking for what is being oxidized, what is being reduced. And then, yeah, another good question that came up when talking about the state, okay, this is something about something else. But someone did email that they put the phase in. And yeah, I didn't put the phase in, so don't worry about the phase when answering these questions. Just what is it? You don't have to worry about is it a solid, liquid, or gas, because again, they typed in the phase because I hadn't written in that as an answer, as part of the answer, right? It just kicked it back. Why do we completely disregard the oxygen? Because oxygen is not participating in this redox reaction. Oxygen is, if we take a look, oxygen is -2 at the start. In the iron 3 oxide, oxygen is -2 in carbon monoxide. Oxygen is also -2 in carbon dioxide. So the oxygen does not participate in this redox reaction. The charge stays the same. So that's why we can get away with balancing this without using oxygen, because oxygen's not gaining or losing any electrons. Ariana, I think I'll come back to that question. State. I think this is like, you're talking like delta H and how like delta H would change if it's a liquid or a solid or a gas.
Yeah, I just wanted to clarify that that's what it meant when it said know the definition of state function.
Oh, like a state function, right? Like our enthalpy is a state function, but I think, yeah, like it would change. Like if I went from liquid water to water vapor, there is an enthalpy associated with that. So even though it's water, water in the liquid form versus water in the gas form would have a different energy, a different delta H associated with it. So yeah, the state concept of changes from initial to final state of the reaction. State function. Oh, okay. State function in the study guide. Yeah, so it doesn't really matter what happens in the middle of the reaction, right? Where did we start in energy? Where did we end in energy? For some reason, I was thinking about phases as well.
No, that makes sense. Thank you.
Maybe because I was thinking about phases for question 11, because that question did come in. We'll get to question 14, and then do we have to write the subscript and our coefficient? No, you don't need the subscript. You don't, or, okay, sorry. You don't need the coefficient. Yes, you need the subscript, because for this to be iron 3 oxide, right, Fe2O3, that needs to be there. That being said, iron is also, you can write in iron, you can write in iron 3 oxide. All of those are possible answers for question 11. All right, 13, then 14 is next. We'll get to 14. For whoever put that in the chat, we'll get there. All right, we mix an aqueous solution of manganese 4 chloride with a solution of silver nitrate, and a white precipitate forms. What is the net ionic equation? Two possible products we can make in this reaction are the manganese nitrate and silver chloride. All nitrates are always soluble. So that's going to be our spectator ion. Chloride will precipitate with silver, mercury, or lead. So that'll be our solid white precipitate. So if manganese and nitrate don't precipitate, there are spectator ions, we can remove them, right? So basically here would be our complete ionic, would be choice B. We're asked for our net ionic. So to go from our complete ionic to our net ionic, oops, no, this would be our complete ionic. Ignore that. All right, manganese on the same side, on both sides, unchanged. Nitrate on both sides, unchanged. I can remove those two. So what's left is silver chloride, react to form a solid silver chloride. And then you just usually put the lowest whole number ratio. So instead of saying 4 silvers, 4 chlorides, 4 silver chlorides, right, our net ionic equation would just be silver reacting with chloride is going to precipitate silver chloride. All right, question 14 that everyone's been, I mean, ChatGTP could have answered question 14 for you. All right, a weak electrolyte is one that, all right, so we talked about strong acids, strong bases. Strong acids and strong bases are strong electrolytes. They ionize completely. All right. Strong acid, base are strong electrolyte. Right? They ionize. Right? 100% they're going to ionize. Whereas our weak acid, right? Our weak acids, our weak bases, they are weak electrolytes. We looked at acetic acid, right? Acetic acid only ionized like 2% in solution. So it only partially ionizes in solution. It's going into solution. It's not reacting, associates, bringing it together. It doesn't disappear. It breaks up into ions in solution. So yeah, our weak electrolytes, they ionize in solution. On the study guide, what properties of electrolytes do we need to know? So yeah, this question right here basically is where we talked about electrolytes. Basically, strong acids, strong bases. They're strong electrolytes. They ionize completely. Weak acids, weak bases are weak electrolytes. They go into solution, but they only ionize part way in solution. All right, we'll squeeze in question 15 here, and then we'll take our break and then get to the next group of questions. All right, a lot of redox reactions, yeah. Following redox reaction is used to heat an MRE. Magnesium reacts with water to form magnesium hydroxide, hydrogen gas, and thankfully it's exothermic. It gives off some heat. Choose the correct statement. All right, so for that, we're going to have to break down, figure out the charge. All right, so magnesium starts off 0, and in magnesium hydroxide, it is 2+. Within the water, all right, I've got 2 hydrogens at +1 each because my oxygen is -2, so that's neutral. We're going to see the same thing in hydroxide. So hydroxide, I can split that up into hydrogen +1, oxygen -2. Right, overall charge is -1. So my charge on hydrogen is the same in water as it is in hydroxide, so that's not going to help us. It's the hydrogen, right? Hydrogen ends up, the diatomic hydrogen ends up as 0 here. So for our 2-half reactions, magnesium starts off 0. Magnesium goes to 2+ by losing 2 electrons. And then how to write this in a way that would make sense. I mean, I guess we could just say I've got 2 hydrogens, 2 protons with water. They each gain 1 electron, and that gives me diatomic hydrogen gas. All right, let's see. So magnesium loses electrons, right? That is oxidation. And the hydrogen gains electrons, so that is reduction. All right. So magnesium is not being reduced. All right, I can cancel out those 2. All right, magnesium is being oxidized. Oxygen is not involved in this reaction, so we can cancel that out. Yeah, magnesium is oxidized, and yeah, hydrogen is being reduced, right? The charge on oxygen stays the same in this reaction, kind of like the previous reaction we looked at. We could ignore oxygen because it's -2 on both sides of this equation. Yeah, Olivia, we can still assign charges, right? So pure elemental solids are always 0. We can assign charges here within water just knowing that the total charge has to equal the charge on the molecule. So water is neutral. Same thing here. We've been doing this all along, right? Magnesium hydroxide, right? The total charge is neutral. The total charge is neutral because I've got magnesium 2 plus, and I've got two hydroxides at -1 each. So +2, -2, the whole thing is neutral. So we can assign charges. We're just assigning them because you're right. They're not aqueous. They're not ions in solution, but we can assign charges to help us understand the reactivity that's taking place, the redox reaction that's taking place. So it is not in solution as ions. That being said, we can assign what the charge would be on each of those elements in the molecule.